Okay, so we're back to 3.2a, annuities, future value. This problem here, number 3, is a sinking fund. It's when instead of buying something and then paying it off, you're saving up for it. So companies do this to just save up to have enough money. They will usually just always rotate it through. So a company estimates that it will have to replace a piece of equipment at a cost of $10,000 in 5 years. To have this money available in 5 years, a sinking fund is established by making fixed monthly payments into an account paying 6% compounded monthly. How much should each payment be? So payment is interchangeable with deposits. It's called a payment just because they are saving up for a particular item, and they're going to also get some interest on it, so they can put a little less in. So they're getting a better deal than if they had to buy something and then pay an interest fee on it, as in like a mortgage or credit card payment. So we have $10,000 is our cost of the equipment. So that is our P sub N. Okay, so that's P sub N is 10,000. We are doing this over 5 years. So N is 5. 6% compounded monthly gives us a rate of 0.06 and a K of 12. So we're going to plug that all into our formula that we've been using. So we would have P sub N is 10,000 equal to D, and then we're going to use the version with the larger parentheses. 1 plus 0.06 over 12 raised to the 5 times 12 minus 1, all divided by 0.06 divided by 12, and then end your parentheses. So how we're going to type this into the calculator, I would type in, start here with the 0.06 divided by 12, then add your 1. Then raise it to the 5 times 12, which is 60. You could just do that out. Then subtract 1. And you should get 0.34885, so on and so forth. And then divide that by your parentheses, 0.06 divided by 12, and then hit enter. Or you could just put in the 0.005 if you want. And you should end up with 10,000 equals D times 69.77 ... I'll continue on. So just leave that in your calculator. Do not hit clear, but hit divide. And then hit second. It's like in the upper left, a green button or blue button, or it may say shift. And then down around your enter key, down the bottom right, there's a little writing, it says ANS, that's your answer key. Mine's above the negative symbol. And hit that, and you should get 143.33. So D equals 143.33. So the answer would be each payment must be $143.33 to have enough, right? So if you are not getting the numbers that I said in the video, let me know. Maybe you can take a little video of what you're pressing. I do show how to hit the keys in there on the videos that I've made already for lessons, but if you just ask, I can make a separate one with a document camera if needed. Just let me know. Okay, now IRAs are things you're going to save up an account. You're going to be putting money in every period. And if you start it early on, it's really helpful, and you can end up with a lot of money in the long run. For instance, like I just get a little bit of money scraped out of my account every pay period, which is twice a month, and my company, this school, matches it nicely, and then I'm building up all this money because I'm earning interest on my interest and putting in bits each month, so it's not making such a big dent, but that is really accruing nicely. So this woman here, Jane, deposits $2,000 a year into an IRA, earning 9% compounded annually. She makes her first deposit on her 24th birthday and her last deposit on her 31st birthday. So that's 8 altogether. So it's over 8 years. K is 1, so they're the total number of compounding is the same. Making no additional deposits. So that's part 1. Now we have part 2. Whatever she makes here, we're going to find a P sub n for that, for part 1. After 8 deposits. Then we have to do part 2, and we are going to use a different formula. We're going to use the compound interest formula that we've used before, a little simpler. P sub n equals P sub 0 times quantity 1 plus R over K to the n K. And then we're going to finish it out until she's 65, so that'll be 34 more payments. So n will be 34 for that one. But the percentage stays the same. So for part 1, we're going to put in the deposits. So we don't have a P sub 0, we have deposits. And then we are going to multiply that by 1 plus what was the percentage? 9%, 0.09 annually, raised to the, it was 8 years times 1, so I'm just going to put an 8, minus 1, all divided by 0.09 over 1, so I'm just going to write 0.09. It's going to make a little divider there. And then P sub n works out to be, I would go 1.09 raised to the 8th equals minus 1 times 2,000 equals divided by 0.09. Then I get $22,056.95. Now this becomes my new P sub O for my initial principal in the compound interest. So I'm going to put that up here. So I'm going to have P sub n for compound interest equals $22,056.95 times 1.09, but instead of 8 this time, it's going to be 34. Remember, K is 1, so I can just write 34. And there's no subtract 1. So I'm just going to go ahead and do this exponent piece first. 1.09 raised to 34. Then I multiply by the 22,000 some odd dollars. And I should get $413,092. It says round to the nearest dollar. So that's what she gets when she's 65. So we'll be in her account when she turns 65. Okay, so do make sure you answer in a sentence. So that's the final answer. You have to do a step to get there. Now, John procrastinates and does not make his first $2,000 deposit until he's 32, but then he continues every month until he's 65. So he's doing 34 deposits in all. If his account also earns 9% compounded annually, how much to the nearest dollar will he have it in his account when he makes his last deposit on his 65th birthday? And you can figure out the interest for each of these. I don't have you do that, but you could compare in that regard, like how much they put in overall versus how much they got out. So Jane has the better deal. So this guy, we're just going to use that first formula here for an annuity. So it's 2,000 times 1.09 to the 8th minus 1. Those outer parentheses over 0.09. And then you'll end up, hopefully you're okay with crunching the numbers now. Oops, I shouldn't have 8 there though. He's doing 34 deposits and all, so 34. And then we will get $393,965 in John's account when he turns 65. So if you think about how much he put in 2,000 times 34. So he put in $68,000, and he gets out $393,965. So that's still pretty good. She put in 2,000 times 8, which is $16,000. And look what she gets out. So she even gets a better deal. I mean, he still did pretty well doing what he did, but Jane, early bird, gets the worm. So I hope you found that helpful. And again, let me know if you want me to show any calculator skills, or you want to show me what you're doing. And also you can come on in and see me or go to the tutoring center too. Sometimes that just is really helpful. Have a great day.